have, as mentioned before, Guy Royse. Am I pronouncing your last name right?
You're pronouncing it perfectly. It's like Rolls-Royce, but without the money.
That's what I thought. You will be telling us a huge story about a lot of technical, interesting, and, buildy, stuffy stuff. But how is it all connected to something that I really relate to, Scooby-Doo?
Jinkies, that's a great question. So I'm basically using Scooby-Doo as an example. So the ridiculous problem I'm solving using machine learning, using recurrent neural networks specifically, is to figure out who said what in an episode of Scooby-Doo. So, give it a line of text and say, was that Daphne or Fred or Velma or Shaggy or Scooby that said it? And so that's what I'm going to show you how it works today, and then and give you enough that you could build something like that yourself as a developer, not as a data scientist. So.
Okay, I'm looking very much forward to that. That sounds like I grew up on Scooby-Doo. This is something like maybe I will even understand some of the technical parts, which I usually don't. Okay, Guy, the stage is yours. I want to hear this so bad.
Happy to share my knowledge. Welcome everyone. I've been introduced already. This is my talk, Mystery Machine Learning. We kind of know what we're doing now. I'm a developer advocate at Redis Labs, or at Redis now. We're no longer Redis Labs. We rebranded to just be Redis because we had a product in Redis and a company called Redis Labs. That was confusing and all that, but you don't really care about that. The important thing is that my boss knows that I told you all that I work for Redis. So thank you. There's actually three things on this slide here that matter. One matters to my boss. I've already talked about that. That's this nice Redis logo here. One matters to me, which is this Twitter ID. Please give me a follow. I have a measure of my own sense of personal worth is based on how many followers I have on Twitter, and it's not in the millions yet, so I just haven't arrived. And the part that you care about, and this is probably the most important part here, it is definitely the most important part here, is this URL to GitHub. All this code and my slides and everything are out there. You're welcome to take this and slice it and dice it and make your own fun stuff out of this. That's where all the code's at, so if you want to play with this at home. So I like this, and whenever I do talk about data science stuff, I always like to preface it with this sort of caveat here. If I was in the audience here, this works better because I could say, who can tell me what this stands for? And I throw a t-shirt out into the crowd. Unfortunately, I'm here in the United States. I wasn't able to travel to meet you all today, so I can't give you t-shirts, and it's hard to do the guessing game. And I think there's about 15 seconds of lag anyhow. So this stands for, I am not a data scientist. I'm a developer. I'm a software developer. I've been writing software for, well, I've got a lot of gray hairs, so you can guess. I'm not a data scientist, and so I'm not an expert. I'm an expert in many ways speaking outside of his field. I'm a fan of data science. I enjoy this. And so what I do is I like to go out and learn about it and figure out how it works. And then I put together a talk and I share with you what I've learned. The benefit of this is I can give a developer perspective on something that can be kind of hard to understand sometimes. The downside of this is that, well, I'm not an expert. So that's my big caveat. I'm not an expert here, but I am a fan. And data science is not the only thing I'm a fan of. I'm also a fan of Scooby-Doo. And I've been watching Scooby-Doo literally my entire life. Well, maybe not literally. I mean, I've done other things, but I've been watching Scooby-Doo since before I can remember, since I was a little kid back in the 70s. And the conceit, the idea behind Scooby-Doo is that there's a mystery to solve. And initially, it looks like it looks supernatural. It's mysterious. It's unknowable, kind of like data science. We look at the problem in Scooby-Doo, and it's, there's the haunted amusement park, or the haunted toy factory. And it turns out it's actually just a man in a mask. It's always just a man in a mask. And data science is kind of like that as well. It's mysterious. It feels like a magic brain in a box, but actually it's just math, and fairly understandable math. And so we're going to go in, and I'm kind of going to try and demystify this a little bit. That's the goal. So mystery machine learning. We've got a mystery to solve. I talked about this during the opening here. We're going to build a neural network. We're going to use data science to tell us who said something in Scooby-Doo, which member of Mr. Inc. said it. The way this is going to work, I'm going to show you how to build an application to do this, right? And just be a little website. I've actually got it running right here. Well, it's not running yet, but I've got, we're going to build this little website here. And so I've got some basic things here. I've got a CSV file with all the lines, not all the lines, but a large collection of lines from Scooby-Doo cartoons and movies and various intellectual properties. This data file is probably copyrighted, but I'm using it. It's data, right? I'm using it for a good purpose. And all this is just a simple CSV file. It's got the column of who said it, Shaggy, Scooby, Velma, Daphne, or Fred, and the line they said. So this is our data set. We're going to take that data set and we're going to use it to build and train a neural network. That's going to be specifically a recurrent neural network. We're going to take that neural network, that model that we end up building, we're going to deploy that to Redis using RedisAI. RedisAI is a module that extends Redis and lets you do model inferencing, do AI inferencing with it. And then we're going to build a JavaScript application on top of that that consumes that model by using a Redis client, and that will tell us who said what. So whether it's Daphne or Fred or Scoob or Shag or Velma. And to learn how to do that, we're going to cover 4 main topics. We're going to cover neural networks. What the heck are they? How they work at a fairly detailed level. We'll get into how they function once they're trained. We're not going to get into how they're trained. That's a much bigger topic that, frankly, I don't fully understand enough calculus to do. But we'll talk about how they function internally so that they become knowable. We'll talk about recurrent neural networks, which is a specialization of sort of the generalized neural network. We're going to show how to build these things using Keras, which is a domain-specific language. It's very semantic. It lets you write code around the ideas of neural networks instead of thinking about a bunch of math. And then we're going to take that model that we build with Keras, and we're going to deploy it on Redis and build a little app around it. And so we're going to talk about some RedisAI and how you can host your models and your AI data used to make inferences with those models on Redis. So let's start with what the heck are neural networks? So you've probably seen this picture before, right? This is a sort of a classic picture that when people talk about neural networks, they always show. It's got these layers of neurons, these nodes. You've got an input layer where all these numbers come in, and you've got a couple hidden layers. So, every node in the hidden layer, input layer, goes to every single node in the layer next to that, next to that. So like node X sub 0 here, where we've got an input coming in, goes to all these neurons here. And then the output of each of these neurons goes to all those. And numbers come in, they kind of flow through the thing. They calculate like, a bunch of relays clicking in an adding machine, and then out spits an output layer with your answer. At their heart, what a neural network really is a function. And I mean that both in primarily in a mathematical sense, but we call them functions in programming as well for a reason, where we put some numbers in and we get some numbers out. And those numbers are used to draw lines. And so we can take those lines, this function draws a line, and we can take that line and we can use it to make predictions. One thing that we can do is we can do what's called classification. We can say, well, what side of the line is our data on? So we've got our X and our Y coming in, or X coming in, or Y coming out. And we can plot, is it over here or is it over here, and determine if it's, above the line and to the left, it's a hot dog. And if it's below the line and to the right, it's not a hot dog. And so this is a way of classifying data. And we can do this multiple times. We can run it through multiple classifiers and then slice it in such a way that we can say, well, it's not a hot dog, it's not Scooby, and it's not Shaggy, and it's not Fred, and it's not Velma, an answer by process of elimination. So one thing you can use these lines for is subdivide a space and say, is it this or that? And we can even look at how close to the line we are when we plot our points. We can say, are we really close to the line? But then we're not super sure. If we're really far from the line, we're very sure. The other thing we can use these lines for is to do what's called regression, or to predict a particular number as opposed to a category. And this is simply, we've done this trick with charts in the past where we look up a value and then we find the corresponding value on the line. So here we have the spookiness level of a particular encounter. Maybe we're going to go to the haunted amusement park, and it's extra spooky because there are clowns. And how many Scooby snacks would it take to get Shaggy and Scooby to overcome their fear of doing that particular encounter? And so we For X, we put in the number of the spookiness level, and then we can draw a line up and over, and then say, oh yeah, that's a spookiness level. That's a 2 Scooby snack sort of mystery. And so this is a way of picking a number. Another classic example of this is housing prices. Have the square footage of a house, or sorry, the square meterage, I guess. And then you have the price of the house. Generally, that draws a relatively straight line. This says the bigger the house, the more it costs, right? And we just draw over. It's the same idea. So that's called regression. So that's what a neural network does. But let's to really understand how a neural network works, let's go down to the lowest level we can. Let's go to the simple neuron, the lowliest neuron, the lonely neuron. This is the simplest neuron we can possibly have. Normally, neurons have several inputs, but we're going to do a single input neuron so we can understand how it works. And so this one has an input of X and an output of Y. And so this neuron is a function. It takes an input, an X, and spits out a Y. And because it takes an X and spits out a Y, we can draw a line with that. We could take all the values for X and run them through the neuron and get all the values for Y and draw a line. Internally, this neuron has a weight that is associated with a particular input. So we have one input, so we have one weight. These are multiplied together. So the input times the weight. And then we have a bias, which is added to that multiplication. And this is all a neuron is doing. Now, getting the values for these weights and biases in a neuron is what training a neural network is, and training the individual neurons is. And that's done using a bunch of calculus. But once they're set, the actual calculations are fairly straightforward. It's just basic arithmetic. In fact, the formula here is just input times the weight plus the bias gives us our output. And if you're astute, and I'm sure many of you are, if not most of you, if not all of you, you might recognize this as being y equals mx plus b, the classic straight line drawing function that we all learned in algebra way, way, way back when we were young. And all we've really done is kind of turn the W upside down, where the weight is really the slope of the line, right? How much it goes to, how much it rotates around the center point. And the bias is the y-intercept. It's sliding that line to the right or the left. And so what these neurons do is they draw lines, straight lines. And so that line could be, like I said, it could have different angles and stuff like that. And, the slope can be different, and the bias, the y-intercept can move, but it's drawing straight lines. So straight lines are all fine and dandy, but a lot of our problems don't really deal with straight lines. And in fact, having straight lines in a neural network means that if one neuron spits out a straight line and then it goes to another neuron which spits out a straight line, you're just adding, when you add two straight lines together, you get another straight line. And so that doesn't really solve a lot of the problems we want. So we need to make these neurons draw non-straight lines. And so the way you can do that is by using an activation function. There's a whole mess of activation functions you can choose from here. I'm going to talk about a couple of them. The simplest activation function, I don't have a nice picture for it, but is it's from the original neural network, the perceptron. And the idea there is either going to spit out a 0 or a 1. And so if you get beyond a certain threshold, you spit out a 1. Otherwise, it's 0. And that's sort of the idea there is that it's activating the neuron. Does the neuron fire or not? So we get some floating points in, and it sort of acts like a logic gate. You either get a 0 or a 1 out, and those feed into the next layer, and then those are multiplied by weights, and then you fire or don't fire. So it's an all or nothing sort of thing. But all or nothing isn't sometimes what you want. What you really need are neurons that can fire at a gradient between 0 and 1. So the harder it fires, the closer to 1 it is, and the more weakly it fires, the closer to 0 it is. And so that activation function of popular choice is a sigmoid. If you want to sort of have a 0 or 1 output, but you want it to be smooth between those, you run it through a sigmoid function. So, your value approaches 0 and it approaches 1. And this works okay. For some applications, it doesn't work very well, particularly the ones we're going to look at today, because you really need things that can fire a little harder than a 1. What happens here is as you approach 1, you have to keep adding that weight. That weight needs to get bigger and bigger and bigger. to push it incrementally smaller distances closer to 1. And so you can sort of get weird floating point things happening there when you start doing the math, because you've got really big numbers being multiplied by really small numbers, and then your precision gets all off, and it can be problematic. But it can work depending on what you're trying to do. Sometimes you want your neurons to not only fire or not fire, but you actually want them to suppress neurons in the next layer. So this neuron is, its output is encouraging the neurons it goes to, but maybe you want it to discourage a particular behavior. If you want to do that, you can, instead of using a sigmoid, you can use a hyperbolic tangent, which goes from -1 to +1. And so it's sort of like fire, anti-fire, right? So this is another activation function you can choose. Recently, I was looking at some artificial life simulations where they're using genetic algorithms. And so they'd have inputs of behavior from the data from the world, and then output behavior like move left, move right, that kind of thing. And whether they want to encourage or discourage those outputs, they were using a hyperbolic tangent function, which worked really well for what they were doing. But by far the most common one that we see is ReLU, the rectified linear units. And this is a fancy way of saying max 0, x. So if x is negative, it's 0. Otherwise, it's x. And so you get this sort of hockey stick shaped line here. And this works really well for a lot of neural networks that simulates the sorts of things people tend to do, like image classification and text, translating text, that sort of thing. So it's a real popular choice, and it's one I'm going to use today. And so that's the activation function. And real neurons in a neural network have multiple inputs. And so, we've been looking at this as a line going through a two-dimensional space, a plane. But the reality of it is that neurons are hyperdimensional. If you got 10 inputs and 1 output, it's an 11-dimensional thing. Those inputs are drawing a 10-dimensional hyperplane that's bisecting an 11-dimensional hyperspace. But the principles and the math are fundamentally the same. It's just harder to visualize. So for example, here in this neuron, we've got 3 inputs with 3 weights. So we multiply the input times the weight, plus the input times the weight, plus the input times the weight, plus the bias, and then feed those through an activation function to get our y. And so here's the math for that. And that's the even more mathy way of representing that using sigma notation. So, but fundamentally, this is still just drawing lines. It's drawing hyperplanes through hyperspace. And so that's how an individual neuron works. So we've got it's kind of fun actually, because if you think about it, we've got this neural network, which is a function that draws lines. It draws hyperplanes through a hyperspace. It's made up of neurons, which are functions, which draw a hyperplane through hyperspace. And then inside of those neurons is an activation function, which then translates it, adjusts that output from being linear to something nonlinear. And when you put these all together, they sort of, it calculates through, and you can get some really interestingly shaped lines. And then you can use those lines to do classification, or you can use those lines to do, regression. So that was Neural Networks in 10 Minutes by Guy Royse. Thank you for attending my TED Talk. So that's kind of cool, actually. I mean, it's neat how they work. But what the heck is a recurrent neural network? Well, a recurrent neural network is a special configuration of a neural network. The picture I was showing you earlier is a fully connected network. It's got a layer of neurons, and they completely connect. Every neuron connects to every other neuron in the next layer, and then all of that layer connects to everything in the next layer. So it's a fully connected feed-forward network. This layer connects to this layer, connects to this layer, connects to this layer, to the output layer. Recurrent neural networks have those same basic things, but they're configured in a special way. So we've got our input layer, just like we do with a regular neural network. We've got our output layer, which is like we do with a regular neural network. But we have multiple hidden layers. And these hidden layers, even though I've drawn them as boxes, are just like the hidden layers in the previous neural network. But we have a series of them in an array. And so the idea behind doing this is that this input data we have here, x0, x1, x2, is got some sort of natural order to it. It's chronological, or has some sequence. And as we, and our outputs can be sequential as well. And as we go through this hidden layer, so we got this hidden layer right here, right? And we got an input. And so we take that input and we run it through a hidden layer and we get an output, just like we did with a feed-forward network. And that output, in this case, we ignore it, but we could capture it. And then we send it to another hidden layer. And so then the next hidden layer has the input of the second piece of data, and it has the conclusion of what was drawn from the previous piece of data, the previous input. So I put in, a value here, maybe it's a stock price. And then it comes to a conclusion about that value. And it says, well, this conclusion goes into the next hidden layer, and then my next bit of data comes in. And now I have some historical context. I know what's happened before in that order. And I can use that as input. The neural network can use that as input to make its next decision. And so then you got these two values come in, and then that feeds into the next one, and then you get the next value in sequence. And so these recurrent neural networks take this chronological data and understand the history of it. It understands all the things that have come before, and that's used in making the next decision. And then at some point, we'll start pulling off these outputs. This particular one I'm showing you here is a many-to-many recurrent neural network. Many-to-many networks are great as translation and machines and chatbots. So, if you think about it, a chatbot and a machine translation is kind of the same thing. I say something, it says something back. It's just that it may or may not be in the same language. So here we've got Shaggy, and he's saying, he's interacting with an online Scoob bot. And he says, look out, Scoob. I can't do a Shaggy impersonation, apologies. And then the Scoob bot responds with, okay, Reggie, which I also can't do a good Scooby-Doo impersonation. I can laugh like Scooby-Doo, however, so well, I'll go ahead and do that now just for everyone's entertainment. Hang on, let me prepare myself. There we go. So many, great for translation, great for chatbots. Look out, Scoob, gives you an appropriate response. I suppose you could build a Scoob bot that just says Roque Reggie all the time, and it would always be the correct response. But that's what a many-to-many is good for. And you've got a one-to-many configuration where you have a single input and multiple outputs. And these are good for generating text. A great example for this is image captioning, where you take the output of a convolutional neural network, which is another type of neural network that's good at image classification, take the elements that it identifies, feed that into a recurrent neural network, and then generate a caption for that image. If you use PowerPoint does this all the time when you drop an image in. That's probably what it's doing behind the scenes. I don't know that for a fact, but it seems likely. And so there we go. Hit the up arrow. So here we have a picture of Daphne, and we want to caption it. Daphne is captioned as saying, "Jeepers, they mean business." I'm not going to even attempt a Daphne impersonation. And so that's one to many. Many to one, which is the one we're going to look at today in greater detail, is good for sentiment analysis. So you can give us some text, and it can say, is this positive or negative? You've probably heard of the example where you take a bunch of Amazon reviews, and then, was this a 5-star review or a 1-star review? And so, it can learn from that data, hey, looking at this text, is this positive or negative? Give me a number from 0 to 1 for positive. 1, thumbs up, totally positive. 0, no, it sucked. And so it does that. It's good for text classification, which is the problem we're going to look at today, where we give it some text and say, who said it? Daphne, Fred, Velma, Shaggy, or Scoob. Or perhaps, a practical application would be emails come into a company and you need to route them to the right department. You could look at the content of the email and say, this should go to customer service, this should go to collections, this should go to tech support, that sort of thing. And you can also use this for predictive text. So, hey, I think this is going to be the next word you type, or the next couple words you type. And so based on all the things you've typed so far. So lots of uses for the many to one. So here's an example of, hey, we provided some text. Hey, gang, let's split up. Who always says that? Fred's always the one that has the brilliant idea of splitting up. So let's look at the many-to-one to classify text. This is what we're going to build today. So we want to take the text, I can't see without my glasses, which is said by Velma. And so that's, I'm going to use this example, but there's some problems with this example so far, right? I said at the very beginning, this is all math, right? This is numbers. These are functions, right? And these neurons are functions. These neural networks are functions. There's activation functions within them. But we've got things that aren't numbers that we're talking about in our neural network. We've got, I can't see without my glasses. These are words, not numbers. We need to turn them into numbers. We've got Velma. Velma is very much a cartoon character and very much not a number. And so how do we turn words and Velma into numbers? We'll start with the words. So the first thing you do is you tokenize the words. Excuse me. And by you, I mean, your software, and Keras will, for the most part, take care of this for you. Tokenizing is you just take your corpus of text. In my case, in our case, the big CSV file with all the Daphne Fred, who said what, and you count up all the words, and you build a little tokenizing table, right? So what this does is it counts all the words. The most common words get the number 1, and the next most common words get the number 2, all the way down until the least common word of zoinks gets the number, the last number you needed to. In our case, 24. So we've got this little 24-word dictionary. This is a substitution cipher. Like A is 1, B is 2, C is 3. The C's are substitution cipher. This is the same idea for words. And so I can't see without my glasses becomes 10, 8, 21, 23, 4, and 3. And if there are any missing words, then those just become zeros. Missing words, here we got a null at the very beginning. That turns into 0, I can't see without my glasses. You might have noticed that my index here for my word tokenization starts with a 1. And that's because 0 is there if a word is missing or if the word is not in the dictionary. And so if it runs into a word it doesn't recognize, it puts a 0 there and just moves on. So this is a way of turning those words into numbers. And so these can be put into our neural network. And so once they're inside of the neural network, these values are one hot encoded. So one hot encoding is this idea of taking that number and treating it as an index. So here we've got the number 0. It doesn't map to anything, but the number 10 is the word I can't see without my glasses. So I is position 10. So it gets a 1 there. The rest of these are 0. So the 1 goes in the column representing that value. The 1 goes in the column where it's hot. And we do this because it makes the math easier. That's really what it boils down to. But what happens here is that when you one hot encode like this, it gets big quick, right? You start getting really large matrices here. And so we'll do another step, and by we, I mean the model, called embedding. And so embedding, you can think of it, there's a couple ways to think of it. Here we create this massive embedding table that says the word glasses is equal to this number here, this 6-digit, this vector with 6 numbers in it. And you say that you can think that the values encode semantics, but what's really happening here is that these are a coordinate system. And so this is a 6-dimensional coordinate system. And words that are close to each other in that 6-dimensional space or that 2-dimensional space or however many dimensions you want to make your embedding are more related to the concept that we're trying to predict. So glasses is a word that's more Velma related than it is perhaps a Scooby related. Whereas Raggy is probably more Scooby related. So all the Scooby words are sort of clustered together in this space, in the 6-dimensional space. And all the Velma words are clustered together, and words that are kind of in between or in between. And so they have a semantic relationship. These coordinates provide that. And these are built automatically by just training your neural network. It happens as part of that process. And so what's really being sent here is those embedded values. So I is this 102.00050, which if we go back to our previous thing, I don't have I in there, but glasses is 1.2.1475 there. And so if we look at glasses, you got the 1.2.1475. And so these values are being put into the neural network, and then the math is being, all that calculation and training is happening. For an output, the output's actually a lot easier. What we get out is a number, a vector here with 5 values in it that add up to 1. And that adding up to 1 is important because it allows us to think of them as percentages. And each of these values simply corresponds to a member of Mystery Incorporated. They're in alphabetical order. So you got Daphne, Fred, Shaggy, Scooby, Velma. And so this is 0.83 for Velma. So it's 83% likely that Velma said, I can't see without my glasses. So that's, this is how these recurrent neural networks work. They take that sort of history and provide context and move it forward. And this is how you can turn your natural language into words into numbers, and then your outputs from numbers back into your classes. Recurrent neural networks have a fundamental problem, which is called the vanishing gradient problem. Vanishing gradients, the vanishing gradient problem is that way over here on the right, to get our final output, this hidden neural network is making its decision based on the context of everything in the past. Half of it comes off of that, and half of it comes off of the word is the last word in the sentence. And so that means half of our decision is made off the word glasses, and half of it is everything else. And then that gets subdivided, and that gets subdivided, and that gets subdivided. So my is then a quarter of it, and without is an eighth of it, and C is a 16th of it, and a 32nd, et cetera, et cetera. And so this means that words that happen very, very early in the sentence tend to be forgotten, even if they're important. And words that come in the end tend to be really important, even if they're slightly out of context. And so the word glasses, if you end a sentence with glasses, it almost always will classify that as Daphne or as Velma. Or if you end it with Scoob, it tends to come up as Shaggy, because Shaggy will say, like, look out, Scoob. And so this is a problem with it. There are some a couple of solutions to this. There's the long short-term memory and the gated recurrent units. I don't know a ton about these. I haven't dived into them in depth. But the gist of them is that they try and, when words are deemed particularly powerful or strong or really important, you hang on to them and then feed them back in later so that it doesn't forget. It's like, no, hang on to that word. It's important. So that's the idea behind them. Transformers are also real popular is really kind of the direction a lot of natural language processes is heading. And so that's a whole nother talk. But that's recurrent neural networks in a nutshell. Let's look at some code here, right? I've sort of gone over a lot of principles, a lot of theory, a lot of ideas on how these things work, but implementing them in code is in many ways a lot easier because Keras. Keras is a domain-specific language, makes it easy to write neural networks. The idea here is that it provides metaphors that you're thinking about when you're creating a neural network as opposed to the math. It's for Python, and it's part of TensorFlow. So you can spit out TensorFlow models when you're done with Keras. Here's a simple feed-forward neural network. We define a model. This is our sort of our model template, I guess you could say. It's a new sequential. Sequential because it's got a layer followed by a layer, followed by a layer, followed by a layer. So in sequence. On that model, we start saying, well, we have our first hidden layer is going to be a dense layer with 5 neurons. So dense 5. That means fully connected. Our activation function is ReLU. We could say sigmoid or hyperbolic tangent. We're going to use ReLU. And we specify our input shape in this first layer as well. And saying these neurons are going to receive 4 inputs with the shape of 4. So it's a one-dimensional with a 4. This is a tuple, so what comma means. So it's a tuple with 1 value. And so we've defined on this first line of code our first hidden layer and our input layer. We want to have another layer here, another hidden layer. So we say dense 5, activation ReLU again. And then we can add our output layer, which is also a dense layer because it's, again, fully connected. But we only want 3 outputs for this instead. And we want our activation to be softmax. Softmax makes it add up to 1. So it's just like we did with the text classification example. We want all our outputs to add up to 1 so we can think of it as a percentage. Once we've added our layers, we can tell the model to compile. We give it an optimizer. This is the thing that adjusts the weights and balances inside of that neural network to make them be more in line with the correct answer. It's part of the back propagation. It's part of the training. We give it a loss function, which is how we measure how wrong we are and which neurons are to blame. And then we have a metrics output, which is for us humans to see the accuracy of the model. We call model.fit, giving it data. X train and Y train is the training data. X is our inputs, Y is our output. So X in our scenario would be all the lines from Scooby-Doo, and Y would be who said it. We give it a batch size of 20, which says go through 20 records before you run the optimizer and calculate the loss, not necessarily in that order. And then epochs of 10, which is go through our entire set of data 10 times. Once we've done that, we can evaluate that model off of testing data that we set aside. We take all of that Scooby data and we use 80% to train it and save 20% to measure how good our model is. And so here we're evaluating it on some data the model hasn't seen. And then we can make predictions passing in values for X. We're passing in lines from Scooby-Doo. A simple RNN is very similar. Got some constants up here. We got a new sequential. But the first layer we add is our embedding layer. This is that hyperdimensional thing where, you know, these words are clustered together in this coordinate space. And we're saying, you know, we want to create an embedding layer. It's got this many dimensions of inputs. It's got this many columns, which is how many dimensions that the actual embedding is, and then how big our lines are. You know, what the length of our input is. We then can add a simple RNN layer, which just creates all of this right here for us. And we just say it's got a number of units equal to the number of embedding columns. And then we can give it an output layer. Here we've added a dense 5 activation of softmax. So this is for the 5 members of Mystery Incorporated. So that's a lot. And I'm running short on time. I'm gonna do a quick demo here and I'm probably gonna have to skip a little bit. But I do wanna show this thing working here. So I've got this build model.py. I'm going to go ahead and say Python build model. And this code's out on GitHub. I just want to show that this model actually, this code using Keras actually does a thing. And so here we go. We're training our model. You can see our accuracy is going up, up, up. Our loss is going down, down, down. That's great. That's what we want. And then it finished here. And when we actually run our evaluation, which is this line right here, we find that our accuracy is actually terrible. And our loss function is really high. And this is classic example of our model being overfit. It's memorized the test data as opposed to understanding the pattern of the data, or memorize the training data. But it's still you know, fun to play with. We can get, like, we pass in Jinkies and it says Velma Dinkley said that. We pass in like hang on Scoob and it concludes that that's Shaggy. We pass in Roque Reggie and it says that's Scooby-Doo. So it knows its catchphrases. This is actually, in a certain level, a fundamentally flawed problem in that a lot of the lines from Scooby-Doo are going to be things that anybody could say. And so it's, in a certain level, not very classifiable. And this is also a good example of why, as a developer, you can build these things and it's fun. But if you want to build these things for like real production data, and I did not show you the demo here. Let me run that again. There we go. But if you run these things as a data, you know, as a developer, you should pair with a data scientist, right? So don't just go out and start doing stuff and deploy it into production, and then bad things can happen. You need to work with someone that has the math background. Let's see, how am I don't have a ton of time left. So I'm going to talk briefly about RedisAI and super quick. I'll just kind of gloss over it. RedisAI is a module. It adds AI features to Redis. In essence, it turns Redis into a model server. Modules are things that sort of like plugins that make Redis do more. This makes Redis a model server. It supports multiple backends, so you can use TensorFlow, PyTorch, or Onyx. And most importantly, it adds 2 new data types to Redis, the tensor and the model. The tensor is your hyperdimensional data structure of numbers, and a model. And I'm going to gloss over these a little bit. But the way it works here is you load a model using model store, you load a tensor using tensor set, you execute that model using model execute, which writes out a tensor, and then you call tensor get to get the model, the output. And so, and the cool thing here is that because it's Redis, these Redis commands can be run by any Redis client that you're using. We're all probably using Redis somewhere. And so this allows us to do things like get to it from JavaScript. I'm going to show you that here really quick. I got a demo for that. Let me go ahead and pull this down here a little bit. I've got Docker and Redis running here. I've built my model. I'm going to go ahead and say npm start. Now I've got a little REST service running that we can hit that will let us do Scooby-Doo classifications. I'm going to do a little web service that will hit that. And I'm going to show off this application. I'm going to show off this application if it's the last thing I do. So here's this little this model that I've just shown you how to build. Here I've deployed that model to RedisAI. I'm going to hit it with just JavaScript code. So I can just type in a line from Scooby-Doo. I'm going to do Jinkies. And here it identifies that as Velma Dinkley. It works. Let's say like look out Scoob. And that identifies it as Shaggy Rogers. I can't see without my glasses. It says that's Velma. If I add Scoob on the end of it, I wonder who it's going to be. If I say like, I can't see without my glasses, Scoob. It's probably going to come back as Shaggy. I don't actually know. It does come back as Shaggy. So this is an example of the vanishing gradient problem. Even if I take the like off there. The model has learned that when sentences end in Scoob, that's Shaggy, even though that might not be correct. So this is an example. If we go back and look at my terminal here, we can see that you know the scores here. So that one here, it was 99% certain that was Shaggy, even though it should have had a much higher score for Velma. This is an example of overfitting, but it also is an example of the vanishing gradient problem. So let's skip ahead here a bit. So I'm going to wrap this up here because I've got about 2 minutes left. You should all have yourself a Scooby snack. I have covered a ton of material in a rather short time here. I talked about neural networks, how they work, recurrent neural networks, how they work. Showed you some Keras code, showed you it actually working. Showed you RedisAI actually working. We didn't get into it too much. That's fine. If you want to check out more on this topic, go out to some of these sites here. You can go to redisai.io and learn about RedisAI. If you want to play with my code, I've got a QR code you can scan here in just a bit. Some Redis-oriented resources here that I'm involved in. We've got free classes. We've got a Discord server that I run, and I make some videos too on this topic. And here's the one you really need. Here's a QR code you can scan to get all the code and all the slides and go check this out on your own. I promise you this QR code will never give you up nor let you down or take you to some site that it's not supposed to. So be assured of that at least. And that's pretty much what I've got. Yeah. My name's Guy, and thanks.
Thank you very much. Then
I think I got time for like one question.
Yeah, you kind of do. Not necessarily if we have questions, actually, because, well, third day, the end, people are basically tired and like to keep it silent and theoretical in their heads. Anyone from the live audience, will you have a question? I almost had my hope when somebody moved there, but he was just adjusting at the backpack. Anyway, I know that online people are, they're having a little bit of a delay. So if they will have questions, they will have them in, 30 seconds at earliest. Anyway.
TikTok, yeah.
Yeah, so we're like spending time just, chatting, just doing nothing. When I see that, I will see that after delay, and that will also take time, and so on. So if nobody from the live audience has any more questions, which is understandable, I mean, come on. You're almost the last one today, and we're all going to the weekend.
That's right. I know I'm going to direct next. So.
Oh, okay. People are finally commenting. They finally saw your session's speech finish. But yeah, so they're saying it's great stuff. Moving over to your Git page, great talk. Everybody's thanking you and so on. No questions seems so far. Anyway, so I'm going to let you go. And thank you once more for this beautiful speech. And, well, just for bringing Scooby-Doo back to the stage. Yeah.
Sorry, I had to.